On what we did last time. We discovered that the derivative with respect to x of the sine of x was equal to the cosine of x. We also discovered that the derivative with respect to x of the cosine of x is equal to the negative sine of x. And the thing to remember there is if you take the derivative of a cofunction, you're going to get a negative in the answer somewhere. Always happens. And I think we actually got to this tangent too.
Yeah, we did.
Derivative of the tangent of x. It's not a cofunction, so it's not negative. It is the secant squared.
We got another one too.
And we got the cotangent too.
We did do cotangent too? Awesome. Okay. Squeeze that in here then. See. Oh, I missed that D. Try again. Got it. All right. Let's add a few more. The derivative with respect to x of the cotangent. It is a cofunction, so it's going to have a negative. And it also gets the cosecant squared. Cosecant squared of x. And did we actually prove that, or did we just guess it?
I think
You just told it to us.
I just told it. Okay, so we didn't prove it yet. All right, so we'll have to do that. So we'll review that, and then other things we're going to do. We're going to take a look at, let's say, how about the secant of x? Oops. And what are we missing? Cotangent?
No, we've got.
Oh no, cosecant. Cosecant of x. So we're going to do those right now, and then we'll play with some more fun and exciting ones. And that did not come out right there. I'm missing a C. There we go. That's what we're going to do there. All right, so let's take a look at the cotangent. And we'll fill in the rest of that chart. So derivative of cotangent. For me, I find it helpful in trigonometry to go back to sine and cosine. So cotangent is equal to what in terms of sine and cosine? Exactly, yeah, the cosine over the sine.
Oh, sorry.
A little slow. It's only Tuesday. So then I can use the quotient rule on this, right? So our low d high, less high d low over low low. All right, low is sine of x. Derivative of high is?
Negative cosine of x.
Derivative of the cosine?
X.
Almost.
Close.
Negative sine of x.
You know what I said?
Well, you said negative cosine.
Oh, sorry.
Yeah, that's okay. Yeah, you're on the right
In my
path there.
head,
Just
it
gets
was
me doing it. Then we're going to have a minus,
Cosine. of
right? The top function, yep, cosine of x, times the derivative of the bottom,
Just cosine of x.
which is cosine x, all over
Squared.
sine squared. So what does that give me? Let's see, both pieces are negative, so I can factor out a -1 from the top. And then what I'm going to have left is the sine squared of x plus the cosine squared of x.
You factored out the negative.
I factored out a negative. Yeah, so this and that are here now. All over sine squared. Now, if anyone's getting excited about canceling that sine squared, that is illegal at the moment, right? But there's a more exciting thing living here. What is it?
The sine squared plus cosine squared can equal to 1.
Yeah, this thing right there is really 1.
Even though it's squared.
That's the Pythagorean identity for sine and cosine. Sine squared plus cosine squared is 1. Now, this is definitely something you want to have committed to memory.
It would be -1, right?
So 1 times -1 is -1. We're going to do lots of trig review. Don't worry. Wait till we get to inverse trig functions. Then it's going to get exciting. So this is -1 over sine squared which I could view as -1 times 1 over sine squared. That's another version of the same thing. And why would I write the 1 over sine separate like that? Because it is really cosecant. So I do now have the opposite of the cosecant squared of x. Cool, we did it without having to use the definition of the derivative.
Are you recording?
Yes, I am. Thank you very much. All right. Ready for another?
Sure, why not?
Excellent. Let's do the cosecant. So cosecant is better known as, or also known as,
1 over sine.
1 over sine, yep. So this would be the derivative with respect to x of 1 over the sine of x. And guess which rule I can use on that?
The quotient.
The quotient rule again. Yeah, the quotient rule is going to be pretty popular. So quotient rule says take low times d high. So low is sine of x. Derivative of 1
Is 0.
is 0. Cool, I love multiplying by 0. Minus high times the derivative of low,
Cosine.
which is cosine.
Yeah, cosine.
All over sine squared. All right, so 0 times sine is 0 on a good day. So it looks like I have -1 times cosine of x over sine squared, which I'm going to write as sine of x times sine of x for just a sec. So we have a co-function we started with, right?
Yeah.
And there's a negative in the answer. I said that was going to happen, so that's good. I didn't lie. Then I have some other things here. For example, I have a 1 over sine in the answer. 1 over sine is known as
Cosecant.
cosecant. So I get a negative cosecant of x in there. And then I have cosine over sine, which is cotangent. So negative cosecant cotangent is the derivative of the cosecant of x.
Oh, okay.
And that's another always.
Yep. So I'm going to go add that to my list back here. Where am I? This guy down there. I give myself quite enough room for that. Try again. Rinky dink. So negative cosecant of x. Oops, I didn't give myself enough room again. Times the cotangent of x. Is that one. Anybody want to take a wild guess at the secant based on what we just saw?
Negative.
Negative secant times.
Not negative, but yeah, I think it's going to be secant tangent, which matches this cosecant cotangent. Let's see. Good guess. So derivative with respect to x of the secant x.
I think it's probably the 1 over outside.
1 over, oh, okay. So secant is also known as what?
1 over cosine.
1 over cosine. All right, I'm going to give you guys a second. Apply the quotient rule to that. You get. So again, low d high minus high d low, low d high, and derivative of 1 is 0, so that part's gone, minus high, which is 1, times d low, which is the negative sign. We get a negative times a negative, which is positive, sine of x, divided by cosine times cosine. And then I can break this up by saying I have a 1 over cosine of x there, and I have a sine of x over cosine of x, which I can rename as secant of x times tangent of x. Yeah, cool. There's patterns to these suckers. It's nice. Helps just to remember them. So adding that to our list of wonderful formulas back here. We get secant of x times tangent of x. Pretty cool, huh?
Oh, it's a leaf blower, I was wrong.
Leaf blower, oh yeah, okay. So let us take a look at some other combination of functions. So let's find the derivative with respect to x of something like x squared plus the sine of x. We're going to combine functions and see what happens. So we have a rule about sums that says we can break it up. So this would be the same as the derivative of x squared plus the derivative of the sine of x. Derivative of x squared is 2x, and the derivative of the sine is cosine of x. Not too bad. What if we multiply those two together? We have to use the product rule, which is a little more exciting than the sum rule.
I think your definition of exciting and our definition of exciting are two totally different things.
They are two different things, yes. My definition of exciting is a little bizarre to some people. Or fun. My definition of fun is a little strange. I got a problem with it in a minute that I thought was wicked fun. All right, so product rule says we have to take the derivative of 1 at a time. So the derivative of x squared is 2x, but leave the sign alone when you do that. And you're going to repeat that process for the other function. Leave the first function alone and take the derivative of the second. And there's really not much we can do to clean this sucker up. We could factor out an x, but I don't think it makes it any better. X times twice the sine plus x times the cosine.
It kind of makes it worse.
Kind of makes it worse, yeah. So usually when I think of simplify, if it's simplified, it should use less ink. I think if we weighed these two, the second one would be a touch heavier. Yeah. So I like this first answer best.
If we put that into the,
I think the system would handle either one. Yeah, if it doesn't and you think you're right, just say, hey, I think my answer's right. Can you check it out? And I'll take a look. All right, let's try another one. How about the derivative? Ooh, it's not right in red right now. Oh, no. It's right in blue. Whoa. Of the sine of x divided by x. Ooh, square bracket. Guess what we have to do here? Quotient rule. Yeah, the x's do not cancel. This x in here is not touchable. It's stuck. Yes, sir.
So can you pull the x out?
No,
No.
you can't. If you tried to factor the x, you would get a sin.
I mean, like, well,
I don't.
X negative 1.
That's bad in math.
No, just no. Just no.
Yeah, the only alternative here, you could rewrite this as the derivative with respect to x of 1 over x times the sine. Those are algebraically equivalent.
That doesn't help you cancel anything.
It doesn't cancel anything, but you could use the product rule instead. So if you like the product rule better, you could do that here. Should we test that out?
Yes.
Okay, so what we're gonna do
Or the other way
is from the middle of the room is between these row of desks. So everybody on the left side here is gonna use the quotient rule.
around. Okay.
Everybody on the right side over here, my right, is gonna use the product rule. So some of you are gonna take this derivative, some of you are gonna take that derivative. I'm gonna do them both, see what happens.
So much enthusiasm.
All right, so let's see. Different colors too. Black. Okay. This one, I think I'd rather keep that to the negative. This works.
I have a question. Can you clear the fraction if it's not set to anything, or does it have to be set to something?
What do you mean? I'm not sure I get the question.
So like, let's say I have two
Like-
different like fractions,
You want to cancel something here?
kind of.
Yeah, so you could view this as the whole difference is being divided by x squared. So you could view it as x, cosine of x over x squared minus sine of x over x squared. And then at least you get to cancel a little bit in the first part. So that would give you cosine of x over x squared, over x, sorry. Minus, but then you're stuck with the x squared over here, and you have two different fractions.
So yeah, but at that bottom part, I can't.
There's nothing that cancels here.
So you can't but clearing the fraction would work.
We mean clearing, but you can't clear the fraction here. You're stuck with those denominators.
You're stuck with this? Okay.
Yes.
Cool.
Yeah. If you had an equation you were trying to
Yeah.
solve,
Okay.
you could multiply both sides by the denominator, but this isn't an equation. We're just simplifying something. Yeah. So I would say, I would stop here, because I don't think this is any simpler down there. I think that uses a little bit more ink. Barely. All right, so this one over here, let's see. I'll write it as x to the negative 1 times the derivative of the sine. It's cosine. Then I take the derivative of this guy, which would be negative x to the negative 2 sine of x. So that's one version of the answer over here. If those negative exponents are bugging anybody, then you would have to rewrite that as the cosine of x over x minus the sine of x over x squared. Does that look familiar?
Yeah, which is what would have got if we
That's
simplified.
what down there. If you want a common denominator here, then you would multiply top and bottom of that sucker by x, in which case you get x cosine of x minus sine of x all over x squared, which is what we have right there. Yeah. So two different ways to do it. I'm not sure which one is easier.
Either.
This one I had to upfront do some algebra to put it to a state where I could apply the product rule. Here I could just directly apply the quotient rule. So, trade-offs. All right, let's do another. What do you think?
We don't use half limit.
I want to take a guess at the answer.
Take out the 2 and multiply by the entire sine of x, so it's 2 times sine of x.
Yeah, so that's a good point. So when it turns out that the sine of 2x does not equal twice the sine of x.
Because isn't it the 2 on the inside determines the period?
It's gonna be
That determines the period, yeah, this is a totally different function, yeah. So this would be a higher amplitude, this is a different period. Yeah, so they're not the same function, they're two different things. So the 2 complicates things greatly. We might say, can't I just take the derivative and say, hey, this is the cosine of 2x?
No.
Well, what about the 2? Do we just not do anything about it? All right, so does anybody remember the double angle formula for sine?
It's
2
a
sine.
2.
Yeah, so this is wrong. You remember it? Tell me it. What is it? 2.
I think it's 2 sine A or be 2 sine 2A.
Half angle formulas?
But you mean
I'm
like a
pretty sure
triangle?
it's twice the sine of x times the cosine of x.
Yes. I was looking
2
at
sine
cheat
A
sheet.
cosine.
Yeah.
You can be right.
Yeah, that is the identity. So having that 2 in there really makes things different. And I can't just ignore it. It changes the derivative. So at this point in time, since I don't have another option, I've got to rewrite it this way. But then I'll show you a trick after. And I have to use the product rule. Okay. So this 2 is just chilling outside. So it's just going to hang around. So I'm just going to put a 2 parentheses. Product rule, derivative of the sine is the cosine times the cosine plus the sine times the derivative of the cosine, which is negative sine of x. Lots of parentheses. So altogether, it looks like, I'm gonna switch colors. I have 2 times parentheses cosine squared of x minus sine squared of x. Oh dear. That is not the Pythagorean identity. That does not equal 1. It does not equal -1.
Wait. Oh yeah, never mind. Sorry.
You should made it worse.
No, I mean, really, right? We want to say cosine times cosine is cosine squared. And I had no choice but to use the product rule, right? Because that 2 is in the way up there, but at least here I got it outside. We could use some identities on that. Does this look familiar to anybody? Cosine squared minus sine squared? Ben's got his cheat sheet there. It's on there somewhere. I believe that's the cosine of 2x. I think that's the cosine double angle formula.
Cosine double angle, cosine squared minus sine squared equals 2 cosine squared minus 1.
That's it, right?
Which is 1 minus 2 cosine squared.
Yeah, those are other versions of it. But yeah, this right here, the thing aside from that 2 right here, this inside part is the cosine of 2x. So here's what we discovered. We discovered that the derivative with respect to x of the sine of 2x is equal to twice the cosine of 2x. Now, that's kind of not a surprise, right? Because isn't the derivative of sine the cosine?
Yeah.
So that we were hoping that would appear. But the 2 not only stayed where it was, but it also popped outside. Oh, my.
And does that hold true for all constants within a, for all whole numbers within a trig function? Like we put 4.
That's a great question. Will this always happen? Like, what if there was a 3 or a 4 in there? What if it was the cosine instead? So if I throw a 3 or a 4 in there, it gets way harder.
Okay.
Because although there is a double angle formula for sine and cosine, there isn't a triple angle formula. You would have to make one.
Okay.
So just for example, if I did say, let's take the derivative of the cosine of 3x, that 3 is in the way there. I don't know what to do with it, so I would have to break it up. One of my only choices to break it up would be to call it something like the cosine of x plus 2x. So I would first have to apply the angle sum formula to that. And then in the angle sum formula, I would have to apply the double angle formula. So we would have a combination of multiple trig identities going at the same time, and we get this nasty expression.
So no.
So this is,
It only applies for 2.
so if this one right here was medium difficulty, this
Yeah.
one right here is hard.
Okay.
And we can do hard stuff. You guys are in calculus. You've done tons of hard stuff in your life, so you can totally handle that. I'm just going to throw a slightly different twist on it. So let's look back at this sine of 2x for a minute, and we're just going to do a little substitution on it. So we're going to let u equal 2x. Okay. So then I have the sine of u. Okay, right? That's not bad. So if I have the sine of u, I could easily take the derivative with respect to u, because u is my current variable, right? And if I do that, then I just get the cosine of u. Whoa, that's cool. But I'm going to look at remember I talked about differentials. This is the differential form of the derivative. I'm going to break up those differentials and write this as the derivative of the sine of u is equal to the cosine of u. And I'm going to throw the du on this side. So now I have to think about, oh, what does du really mean? Well, what does d mean right here? It means take the derivative, right? So guess what that d means right there? Take the derivative of u. Okay, well, we can do that because we know what u is. So if I wanted to take the derivative of u, u is really 2x. And since there's an x there, I should probably take the derivative with respect to x. And what's the derivative of 2x?
2.
It's just 2. And if I view this in the differential form, then I would say the derivative of 2x is 2 dx. So what does du really equal?
2 dx.
2 dx. So that 2 popped out. What if it was a 3 instead? Guess what would happen?
It would do the same thing.
It would just pop out. Yeah, so if we threw a 3 in here instead, 3, 3, it just puts a 3 here and a 3 there and a 3 there. The 3 would pop out.
Okay.
So what I end up with, really, if you think about it, the cosine of u came from taking the derivative of the sine. So what I have is the derivative of the sine of u times du. I get this chain of derivatives. Yeah, which is the next section. So this is a very nice example to look at, yeah. So we'll get into that a little later. Let's do another example. We're going to test to see, now we have a derivative here for the sine of 2x. We think it's twice the cosine of 2x. It was rather complicated to accomplish. We could have screwed that up. How do we know it's right? Does everything I do come out right?
No.
No, definitely not. So I got to test this. So the way I'm going to test it is I'm going to make a tangent line and test it. So we're going to consider the function f of x equals the sine of 2x. 2x, oh gosh, that didn't go well. 2x. And we're going to find a tangent line at x equals pi over, I think 3 is what I was excited about earlier. Yes, I thought that was a cute one. So just a quick sketch of this before we act on it. If you were to graph the sine normally starts here and it scoots up and goes down and goes back up and it just repeats that cycle over and over again. Normally the period is 2 pi, but since I have a multiple of 2, that cuts the period in half. It cuts it in half, it turns out, yeah. So the period of this thing is really only pi, which means the middle of the wave happens where? Pi over 2, 1/2 pi, yeah. And this peak would happen where? That's a 2. That would happen at pi over 4. So based on that, I believe pi over 3 is going to be about right here-ish. It's not exact. It's not in the middle. It's somewhere in the middle, but not exactly in the middle. You know what I mean? So I'm trying to find that tangent line. For that to come up good, but close enough. Let's do it. So we believe that the slope function, let's do that in blue, f prime of x, our slope generator, is twice the cosine of 2 theta based on our earlier work, or 2x, sorry. So then the slope in this case, m, would be f prime evaluated at pi over 3. So that would be twice the cosine of 2 pi over 3. I'm going to avoid using a calculator for just a little bit longer. Let's see, 2 pi over 3. What the heck is the cosine of 2 pi over 3? This would be 1 pi over 3 there. 2 pi over 3 would be over here. Cosine is an x value. I think it is negative 1/2.
Yeah.
I think it's negative 1/2. So then I have 2 times that. So what do I think the slope is here? I think it's negative 1. Right? Be a good idea to whip out a calculator to test that idea now, right? Okay, so I have the slope. I need a point to throw that slope at. So the question is, what is that point? Well, f of pi over 3 would be the sine of 2 pi over 3, which if this is negative 1/2, then the y value up there would be what? Anybody remember? Square root of 3 over 2. Yeah. So the y value should be the square root of 3 over 2. So putting that all together, I think my blue tangent line would be y minus square root of 3 over 2 equals the slope, negative 1, times x minus pi over 3. Oops, I'm in trouble with minuses today. I think that's the equation of the tangent line there.
Isn't the function supposed to be sine of 2x?
Yep. Did I make a mistake somewhere?
No. I thought it was 2 pi over 3.
We have sine 2 pi over 3, then at the bottom you have x minus pi over 3.
Yeah, so the sine of that, so I plug in pi over 3, so I get 2 pi over 3 there. Sine of 2 pi over 3, I'm pretty sure, square root of 3 over 2. Yeah, I think that's right. Let's graph it and see. Whip out your graphing thingies. I'm going to use Desmos. So my original function is the sine of 2x. There's that wavy thing. Zoom in a touch. All right, and then I'm concerned about the points pi over 3, comma f of pi over 3. Oops, wrong place. Which is, yep, that's kind of close to where I thought it would be. And I think the tangent line, if I got all this right, is y minus the square root of 3 over 2 equal to negative 1 times x minus pi over 3. Oh, I did it. Oh, I did it on the screen too. Wow. Minus. I think I did it. That looks pretty darn tangent, doesn't it? Right there. Cool. So that was just as hard as finding the derivative, wasn't it? I think it was, right? That was quite a bit of work to do there. And here was, where'd it go? Oh, did I mix up my graphs? What's the derivation of that sucker? Somehow my notes get out of order. Oh, there it is. Nope, that's not it. There it is. All right, let's do another one. Does anybody have a homework problem they want to look at?
6 on 3.5.
6, 3, 5. Ooh, that's a beauty. Okay, let's do it. I'll fix my notes later. New page, screenshots. Oh, meant to drag it. There we go. A pet peeve of mine is when people don't put parentheses like that, because those guys are functions, and functions are supposed to have parentheses. So, my apologies that many of the homework problems lack parentheses on their trig functions. I'm going to write to the authors and say, please fix that.
No, and it's weird because even though they don't have parentheses on them, when you type them in, they won't even have parentheses.
In the system, yeah.
Yeah.
Because it's a function, you're supposed to have parentheses, right? So, anyway, what's going on here? We have a product and we have a quotient. So we have to do both the product rule and the quotient rule. So we just have to approach this with caution. So I'm gonna do it in stages. So ultimately, I'm gonna need the derivative with respect to x of that high function. For the quotient rule, that's gonna pop up. So I'm just gonna separately calculate the derivative with respect to x of 2x squared times the tangent of x. And then I'll do the quotient rule involving the secant next. So let's see, for the product rule on that, I would say I would start with the 2x squared, its derivative is 4x. Tangent gets held in check for a moment. Then I hold the first function and take the derivative of the tangent, which is secant squared, nice. Secant squared of x. For sure, I need you to memorize the derivatives of sine, cosine, and tangent. Once you know them, you can calculate the others if you don't remember them. But you got to know those, otherwise life will be painful. And you know, I could factor out a 2x, but I don't think that's going to make my life any better. So that's the derivative of the top function. Right there. So now I can apply the quotient rule to the whole thing. So that's just a stage in the derivative. I'm going to switch to black here. So the, let's see, the quotient rule says take the low function times d high. So low is just secant of x. But then I have to multiply it by all of that. So parentheses 4x tangent of x plus 2x squared secant squared of x. And then I can go minus, it looks like I'm going to run out of room here. Let's tighten this up just a touch. Minus the high function, well, that's easy to write down. I can just copy it, 2x squared tangent of x, times the derivative of the secant, which is secant tangent. Oh, I didn't quite leave enough room. Secant of x times tangent of x. And all of that is divided by secant squared of x. And now we hope we can clean this up. So I'm going to copy this to a new window, capture it all. Get it? Almost. I missed those parentheses. Oh well, close enough. Oh, and that bar. That's okay. We can fill those in. Control C, new page, Control V. So here's where we're at. Oops.
You moved it right off the page.
Okay. So filling in parentheses in that bar. I guess I'm going to have to distribute that secant.
Or secant tangent.
When you take a
Because then you
secant,
Can't you
Oh, I
factor
could-
secant out?
I could factor, that's a good point. That's another option. Let's see. So again, in a complicated expression, there's going to be many routes. We could say, I have this secant here, and that secant here can be factored out of the difference. And that'll cancel with one of these in the bottom. That's a better idea. Yeah, let's do that. So I'm going to factor that secant out. And that is going to leave behind this minus that part. So 4x tangent of x plus 2x squared secant squared of x minus 2x squared tangent squared. Is that okay?
Mm-hmm.
Tangent squared of x all over secant squared, which I'm now going to say this secant cancels one of those. And let's see, what can we do with this here? So now I have to figure out, can I do anything with that?
Factor out of 2x.
We could factor a 2x out of all of that. Something that's catching my eye is right here. Notice I have a 2x squared and a 2x squared, which if I took the 2x squared out of that portion would leave secant squared minus tangent squared. The secant squared minus tangent squared look familiar to anybody? Anytime you have squared trig function, you should think, ooh, Pythagorean identity. Is that in your cheat sheet, Ben? No? Okay. So I'm just going to look up trig identities, and I bet we're going to find that sucker online. Trig identities. Purple math. Let's check out purple math. Oh, purple math says, blow that up. Tangent squared plus 1 is the secant squared. Well, what if we bring that 1 over to the other side and subtract the secant squared? Let's see, what does this one say? Or do I want to go the other way? Secant minus tangent. I want to go the other way. Oops.
Or the positive one then.
So if I leave the 1 there and subtract the tangent squared over, I get secant squared minus tangent squared, which is exactly what I have right here. So this must be equal to 1. Ooh, that's nice. Okay. So what does that mean for us algebraically?
That problem gonna be easier.
Yeah, so it means that since this minus that is 1, all that's left is the 2x squared from that.
But those cancel each other out.
No, they don't. They don't. So what I have right now is I have 4x tangent of x.
2x squared.
I'm going to check it. Hang on, slow down. I'm going to factor that 2x squared out just from that part.
Since you factored it
Oh,
which
you
leaves
factoring it out.
secant
Okay,
squared of
okay,
x minus tangent squared of x, right?
I see.
So I'm going to get 1 times the 2x squared.
Got
So now, switching colors again. Boy, this was a good problem. Thanks for asking, Sam. Here we go. I have now 4x tangent of x plus 2x squared times 1, which is 2x squared, all over secant of x.
Yeah.
And we could play around with, simplifying secant over tangent, but then we would have a 1 over secant. We could turn this into sines and cosines. I'm kind of curious about that. Do we have 1 minute? Or are we out of time?
No, we're
We're out of time.
I tried mine into
You turn it into sines and cosines?
sines and cosines.
Yeah, I think it might actually get a little bit easier if we do sines and cosines, but you have a lot of work to get it to be easier. So we're going to stop with this version right here. You get another day to finish up your 3.5 homework, so get busy. Tomorrow we are starting section 6, which is the chain rule, which is like the most powerful derivative rule in the universe.
Isn't it also like the triple product rule or
triple product rule. There is a triple product rule, but
Oh.
it's not something you need to memorize.
Oh, that would not.
Because I was trying
Maybe
to
we'll
figure
do
out,
one of those tomorrow.
I was trying to figure out how to do that one, like one of the things where it was like three things multiplied by each other. And you
Yeah,
have to,
I'll write up something about that and post it for everybody. Yeah, there is a triple product. It's not worth
Do you
memorizing.
want it?
Oh, is that your fundraising thing? Cool.
It's open on it's like the last page that opens up.
Okay. All right. Carter, hope you had some good